Hello, hello. Excuse me. Sorry. Good morning, good afternoon, good afternoon. Um, okay, good afternoon, Alfred. Thank you. He's often so good on the good afternoon thing. Thank you, Alfred, for saying so. And who did I just? Oh, and he just did I just kick him out accidentally? Wait, what's going on? Okay. Um, yes, good afternoon, Alfred. Oh, right, with the crazy avatar. Okay, and here we go. All right, awesome. Not crazy, I shouldn't say crazy, just intense. Good afternoon, Gabriella. Thank you. Good afternoon, Yanelli. Good afternoon, Kaya. Excellent. Good afternoon, Erica. Awesome. Good afternoon, Ariana. Good afternoon, Andre. Nice to see you again. Good afternoon, Samantha. Awesome. Okay, good to see you all. And anybody who and Sonam, and Skylar. Okay. Hello, hello. Okay. So much to do today. We're going to do one big, thick problem today. One problem, but it's thick and important, and it'll help you for your exam. So quickly to remind you or to review or whatever. Uh, so we have this exam coming up, right? Like it'll be posted Thursday evening. Unfortunately, Halloween. I apologize. It'll be posted Thursday evening. Then you will do it all weekend, and you'll return it submit it on time right before class on Monday, and then you'll come to class. And if you anticipate that you're going to have any issue, like a medical issue, or that you're going to let me know, and we'll deal with and if it's legitimate and I can deal with you personally or privately, like I will. But if I don't hear from somebody or there's, then the exam cannot come in late. And you have to come to class, like if there's no special circumstance that you communicated about. Okay. Anyway, so the way to study for the exam is to deal with the practice exam. The practice exam that's in Google Classroom is bigger and longer than your actual exam. Like it might even seem kind of scary to you, maybe. The important thing to realize is like if you can do everything in that practice exam, then you are set for your actual exam. Like that is a I mean, that's a promise that nothing is going to appear in your actual exam that you don't see somewhere in that practice document. There's not going to be some and similarly, not everything that you see in the practice document will be on your exam. Your exam will be somehow shorter, even if it's because you have choices or something like that. So if you can do everything in the practice exam by the time of your exam, then you are set for your exam. And that's the way to study is to try to do the problems in the practice where try them on your own wherever you can't do something, of course. Look up old videos, et cetera, or look up whatever resources you want for help in any of those problems. And again, it certainly in terms of our channel, our class channel, like if you look hard enough, you will find that I've walked through every one of those problems at some point or another, whether it's last semester or a prior semester. You can find me walking through those problems for help. And then your actual exam will look very similar to that. However, or not however, and like those are the hardest versions. Like by the time we're getting to this exam or the practice exam, what you see in the document are like the accumulated hardest, thickest, most involved versions of whatever concepts are going on in there. So obviously, if you have time and you want to build up to that, that's what all the homeworks are for. Like if you want different variations or exercises that help you build up the concepts, that's what the initial homeworks are for, particularly the ones that we've gone over, which you could still resubmit for more points and all of that. I'm saying all this to say, I'm saying all this to warn you of, or to introduce what we're going to do today in class. Here's the deal. Well, let me back up for a second. Obviously, at any point today or Wednesday, if you have any questions about that practice document, I definitely, this is the time, this is the day, and Wednesday is the day to put them in the chat or raise your hand or whatever and ask me any questions or confusions about the practice document. The more specific and the more concrete the more focused the question, the more quickly I can answer it in class, and the more of them I can answer in class. And at worst, if the question's too broad or too big and I don't think I have time, I'll honestly just say, okay, I don't actually have time to do that right now, but but I'm sure I did it in a video somewhere, or we could set up an appointment or something like that. But what I'm getting at is this. I'm here to try to make your life as successful and manageable for the exam as possible. So last class, what we did in the material is we learned how to add together two displacement vectors, right? We're now in the material, we're like moving forward into two dimensions, right? So we learned how to use vectors to represent two-dimensional motions. And specifically, when we're talking about displacements, we learned how to add together two-dimensional displacement vectors. That's what we did last class. What I was saying repeatedly during that class is the reason we start with displacement vectors is once we know how to add displacement vectors, then the method, the mathematics for adding vectors together is the same for all vectors moving forward, whether they're velocity vectors, acceleration vectors, force vectors, electric field vectors. Vectors add together by the same method all the time. And that method is the component method. By breaking vectors into their individual one-dimensional components. So what today we're going to see is how to apply that method, or what it means to apply that method to adding together two velocity vectors. That's what we're going to do today. And let me say a little bit more about that, and then we're going to do it. I mean, obviously, that's what's on the board right here. It's trying to illustrate the idea of adding two velocity vectors. Okay, a couple of things. Remember, a vector is an arrow that represents a vector quantity. The size of the arrow represents the magnitude of the vector quantity. The orientation of the arrow represents the direction of the vector quantity. When you're looking at and adding displacement vectors, it's somewhat comparatively straightforward, as you saw in lab 3, because a displacement arrow written on the page represents a distance and direction in real space, in the real world. So the length of the arrow on the page represents the magnitude of the displacement vector in real space, i.e. the length of the vector on the page. When you're talking about displacements, the length of the vector on the page represents an actual length, like a distance in real space. So whatever you're drawing as your pictures kind of is the picture of what's like actually happening in the world. Excuse me. So today, though, we're going to be putting velocity vectors together, and the method is the same. The mathematics is the same, are the same. But what we're doing is a little bit more conceptually abstract. So the first thing I want, like notice this triangle, like right in the middle of the screen right here, like the two white arrows putting together to make a dotted horizontal red arrow. What's happening there is just like what we did last class. Like we're saying, if you want to add together two velocity vectors and depict that in some sort of picture, you would put them tip to tail, just like we did on Wednesday. If you put arrow number 1's tip next to arrow number 2's tail, then the arrow that would complete the triangle, the third and final dotted arrow, that represents the sum of the first two arrows, just like on Wednesday. So we're going to do the same math as we did Wednesday. But what it's going to mean now in physical space is very different. First thing to realize And we're going to do this all concretely in a minute. We're going to do a big, thick example in a minute that will help you for the exam. And it's an example taken from the practice exam, excuse me. So the first thing to notice, and like I would write this down in your notes if you can. I mean, I don't want to crowd this whole picture here, but first thing to notice is that each one of these arrows has a length, just like Wednesday, but the length represents the magnitude of the velocity vector now. So a longer arrow, like that arrow that says VAB, that's like longer than the arrow that says VBC. It's longer. It doesn't, now that we're talking about velocities, it doesn't mean that someone walked farther. It doesn't have anything to do with how far. I have no idea how far anybody got if I'm looking at velocity vectors or a velocity triangle. What that long arrow VAB is representing now is that at the point of space and time that could be imagined to be at the tail of that vector, if you imagine a moment in time and a certain location in space, that some object right at that moment was instantaneously moving in a certain direction at a certain speed. In other words, a very long arrow, if it's a velocity arrow, means that at a certain moment, someone's going very fast at that moment. And a short arrow means they're going very slow. It's the arrow. So now these arrows, their lengths are representing speeds, instantaneous speeds. I just want to make that clear. Not average speeds, instantaneous speeds. So I have no idea where someone is or how far they've gotten if I'm looking at velocity vectors now. I just know the rate at which they're traveling and in what direction. That's point number one. So velocity vectors represent instantaneous rates of motion. That's number one. Okay. Again, we're going to put them together with the same math as we used Wednesday, but what it means is now different physically. Number two, I'm putting together arrows tip to tail to add them. But what does it mean to add velocity vectors? Like, it doesn't mean you're traveling that much farther or something like that, because I have no idea how far you're traveling. What it means to add velocity vectors comes from Galileo's principle, form number 4, case 3. Like, seriously. Like the thing that you watched a video about 2 weeks ago, and then a lot of people wrote very, very, very persuasively wrote like, I get what you're doing in this video, but I don't get how this would apply to any concrete problem. Like, how would I solve a problem using this? Right? Like, very fair. They're like, Galileo's principal relativity form number 4, case number 3, is this thing written right here in white, like at the top of the page right here. VAC equals VAB plus VBC. Like, what does that mean? What does that mean? It means, okay, when we add velocities, we have to, for it to be meaningful in the physical world, we have to take into account the relational character of velocities. Every velocity, I'm sorry, even on the internet, I really should cover my mouth, shouldn't I? Can you imagine someday what, okay, anyway. You can't just add, you could add numbers together and get new numbers. But if they're velocity numbers, you have to be careful about which velocities you're adding to which if you want it to mean anything in the physical world. So it's saying every velocity is really a relation between two objects, not a property of one. And that's why once we're getting careful and proper like this, whenever we write down velocities, we always put 2 subscripts after each velocity, because each velocity is a relationship, a comparison between two objects. What are A, B, and C? A, B, and C are any 3 random distinct objects that we're tracking. Like, it could be anything. And in a minute, they're going to be like a boat and some water and a shore, but they could be anything. And what VAC equals VAB plus VBC means is if you want to add velocities together and get an answer that means something in the physical world, you have to add velocities from different frames of reference. You have to add velocities that are being compared to 2 different things, and you have to add them in a certain order. Now, everybody knows this in English. If you go to the simplest case, in the simplest extreme case of this idea, the thing I was talking about in the video, the extreme case is the velocity of me relative to the subway plus, so in other words, imagine objects A, B, and C are A is me, B is a subway, and C is New York City streets. It's like Manhattan, the ground of Manhattan, okay? The velocity of me relative to the subway plus the velocity of the subway relative to Manhattan equals the velocity of me relative to Manhattan, right? Like those velocities add. They add so meaningfully and so accurately that it's why I take subways, right? Or why you take subway, because the velocity of me plus the relative to the subway plus the velocity of the subway relative to the outside streets equals the velocity of me relative to outside streets, like A to B plus B to C equals A to C, meaning I can stand on the subway and I could be going 0 miles an hour relative to the subway, right? Or I mean, I could sit on the subway. I'm not moving relative to the subway. If I look at the walls of the subway, they're not going past me, right? Or the person sitting next to me, they're not advancing past me or behind me. Like relative to the subway, I'm just sitting still and I'm taking a rest and I'm praying and meditating on the subway, right? So I'm going 0 relative to the subway. However, the subway is going 80 miles an hour, whatever, 50 miles an hour relative to Manhattan. Now, it's not going 50 miles an hour relative to me, and it's not going 50 miles an hour relative to the sun. It's going 50 miles an hour relative to Manhattan. But that's what I care about. I'm going 0 relative to it. It's going 50 relative to Manhattan. Therefore, 0 plus 50 equals 50. Therefore, I'm going 50 miles an hour relative to Manhattan without doing anything, right? So you know that's why I take the subway. But so you know that in the extreme case when there's zeros involved and all positive numbers and it's all in a line. What I'm trying to tell you here in physics, and we're going to see this now in a much more complicated, is that idea is it doesn't matter if I'm attached to the subway or not. It's still true. It doesn't matter if there's even if there's negative signs, it's true. Like if I start walking backwards on the subway, right? Or you know this, if you go to the mall and you start walking up the down escalator, if the down escalator is going 5 miles an hour relative to the mall, but you're so negative going down. So say -5 relative to the mall, you're walking up the escalator at +2, then you know you're actually going at -3 relative to the mall. If someone watched you trying to go up the down escalator, but you're not going as fast as it, they're going to see you heading down. Right? The negative, in other words, the velocities add even when negative signs are involved, and even when none of the numbers is 0. And now I'm trying to say it works even if you're in 2 dimensions. When it starts becoming very hard to picture and maybe believe, what we're going to see today in the calculation we do is that idea that the velocity of one thing relative to a second plus the velocity of the second relative to a third equals the velocity of the first relative to the third. That's true even in 2 dimensions. It's true, and it's the only thing that's true. Like if you want to add velocities, you have to add velocities from different frames of reference in that way. And if it's in 2 dimensions, you have to take into account vectors and vector components in order to do it. So what I'm saying is, and which means ultimately you have to make an XY chart, like what you see in blue here at the bottom of the page. You have to do them. So we're going to do in a minute, like now when I turn the page, we're going to do a big, thick addition of velocity vector problem in 2 dimensions. We're going to do just like the same math we did on Wednesday. Wednesday, we added together 2 two-dimensional displacement vectors. Today, we're going to add together 2 two-dimensional velocity vectors. Hopefully, you'll see it. We're using the same math. We're using the same technique. But what it's representing now, what it's meaning, is how different objects observe different motions. So it's harder to picture or harder to conceptualize. That's what we're going to do. Now, I'm almost done with like the intro, so to speak. Homework. We were up to, we were going through problems we've done, as you see more and more in the course now, we don't go walk through every single bit of every single problem. Like we're moving faster and faster now because the idea is now you've gotten the fundamentals. We spent a long time on fundamentals. If you really take the fundamentals and the method seriously, then more and more you get good at applying the fundamentals on your own. So we're not going through every single bit of every single homework problem anymore, but we're still tracking the material in the curriculum. So like what I'm trying to say is we had done a bunch from homework 6, the big old duck. Then it went to homework 7, space relations. If you look back at homework 7, and you could still be revising it and uploading it, especially based on what we do today. Like if you did it at all on time, you got a lot of points. You could still get the rest of the points by watching what we do today and Wednesday. But if you look back, it'll start seeming less and less difficult to you as you look back on it. And if you look back on it, you'll see that there's a lot of excuse me, there's a lot of exercises in homework 7 that are building and building. They're like trying to establish the concept of velocity. Well, first they're trying to establish displacements in one dimension, then velocities in one dimension, then displacements in 2 dimension, then velocity in 2 dimension. It's building and building and building all the way to the point where by the second to last page in homework 7, it's talking about like a Toyota and a Audi, or like these two, or Pontiac and a Toyota. And it's got it's got 3 objects by the end on the second to last page of homework 7. You got 3 objects that you're dealing with: a Toyota, a Pontiac, and a highway. And they each have different speeds relative to one another. And it's and they're all in 2 dimensions with angles and everything. And it's ultimately asking you to add those velocities together to get a final third velocity in 2 dimensions. That's the concept I'm talking about now, like the second to last page of homework 7. All the exercises before that are sort of trying to guide you and build you to that. What I could do right now is go over the Toyota Pontiac problem and like walk you through the answers and all of that. I could, but I think you'll find it much more useful. I think you'll find it much more direct and helpful and useful if I leave that to you as an exercise to go back and review if you want more practice. What I'm going to do is go walk you through right now. I'm going to do a different screen share here. Excuse me. I'm going to walk you through the problem of this kind that's in the practice exam. Okay. Now, again, like I said, I'm not promising that I'm walking through every bit of the practice exam for you. I am promising that you can find walkthroughs of everything somewhere in the channel if you just look hard enough. But I am telling you that right now, I'm like starting now, we still have like almost an hour left. I'm taking what I consider to be one of what right now is one of the hardest problems in the practice exam. One of the biggest, hardest, and newest material pieces of the practice exam is this page that you're seeing on the screen, page 6, part 3, velocity and acceleration vectors in 2 dimensions. Like that's what we've been building toward in all the lectures and everything. It's the next step in the material. This is one of the thickest, hardest problems in the practice exam. I'm going to spend this period walking through it with you now. So now you may not get it right. Like I'm going to go a little fast once I start. It may not all sink in right away. It might for some of you, obviously, or it might be obvious already to some of you. That's fine. But for some of you, it still might be a little intimidating, but I'm going to walk through it now. Obviously, then take it home and use it as a guide or play it slower or let it sink in. And, my best recommendation is like try now, once this class is over, when you get a chance, try to solve this problem on your own without looking at it. See if this class benefited you at all. But like to the extent that you get stuck or whatever, then, look at the PDF and play the video slowly until you can understand what's going on in this problem. Once you get to the point of really mastering this problem, you're a big leg up on the whole exam. Like there's still some other bits that are hard, but a lot of the rest of the exam is meant to build up to this. So that's why I'm going to do it right now. Okay, so I'm saying, just again, so that you know where we're at. This problem is just like the Toyota and Pontiac situation on the second to last page of homework 7. So the flip side is, when I'm done with all this, if it all makes sense to you and you get it and you realize that you didn't know what you were doing, it's possible you didn't know what you were doing with the Toyota and the Pontiac when it was assigned or whatever. Of course, you can use this to go back and fix all that and resubmit that and get all those points. Like that's okay. And it will also help you practice for the exam. But to practice directly for the exam, I'm now going to walk through page 6 of the practice. And again, on your actual exam, of course, I'll change some of the details. I'll change some of the numbers. I won't, but it'll be very similar. You'll have a problem on your exam that's very similar to this one. So you want to know how to do it. Okay, so this is what I'm going to walk through right now. This thing that you're seeing, and you can screenshot it or whatever, but obviously you have it. this whole page here. And I'm also going to warn you, just so you know how to listen, like as is the case with most exam problems, like it's a big situation. It's broken up into a bunch of parts. The early parts are not meant to be tricks. Generally speaking, you have a big situation and generally in a physics problem, you have a situation and you're ultimately trying to answer something important and difficult about it. And that's ultimately usually one of the last parts that you get to. So ultimately, the way physics problems are designed, especially on exams, is they break up the situation into a bunch of steps for you, or I break up into a bunch of steps for you. So the early questions, the early parts of a physics problem are often little pieces that you need to be paying attention to and you need to establish to put together for the big answer coming at the end. Which what I'm trying to say is, yes, it all ties together. It should all flow. Things should fit together. You'll know if you find yourself using answers from part B in order to answer part D, you're probably doing something very, very correct. Number one. Number two, pardon me for a second. Number two, if you find the first couple of questions, the first couple of parts don't seem almost like if you're a little scared because they seem a little bit straightforward or a little bit easy, don't second guess yourself. The first couple of parts in a physics question, don't think that they're trick questions or overthink them or anything. They're usually asking you things that you need to establish in order to do the rest. So if they seem comparatively easy or comparatively quick, that's also probably a good sign that you're doing okay. But then you're going to put the pieces together and do something big. So in this problem here, I'm going to walk through it with the step method and stuff. I'm going to tell you right now, like A, B, and C, once you get what they're asking, they're not meant to be tricks. They're not that hard, A, B, and C, once you get it. But all the real work and the hard part and where you would get the most of the points and where the most of the points could be taken off would really be part D, really D. D is the heart of the problem. Then E and F and G are more stuff about that that are also not easy. But the main heart of the problem is D, and that's all I'm going to have time to do today. Again, you could find videos to do the rest, whatever. But D is the heart of it. If you could do that, that's a very important piece of physics. So that's what I'm going to get to today. Wait, and lastly, and yes, when you do your exam, you have to do today. I'll start by labeling my steps, and then the clock will be ticking. I'll start moving faster and faster, and I won't be labeling my steps anymore. You have to provide all steps all the way in your exam. That's what you're getting points for, is the steps. So okay, all right. All that said, I'm going to switch. Wait, is it clear? So I'm going to walk through this problem from your practice exam, like right now. So and please stop me if it's not, just electronic hands. Is it clear what I'm about to try to do or do? Are you with me? Could you just raise your electronic hand if it's clear that I'm about to do a walkthrough? Okay. Thank you. Awesome. Totally appreciate it. Great. Thank you. All right. I believe you. Thank you, guys. All right. So I'm stopping the share. Stop the share. Stop sharing. Okay. And I'm going to share the thing and start doing it. Okay. Okay. Ooh. Okay. Okay. So that's just an overview of what we're doing today, but okay. But here we're going to, hello. Okay. Yeah. So it's practice exam, part 3, page 6. Again, on your actual exam, it'll look very similar to this. So what the topic is velocity vector addition in 2 dimensions. That's what we're doing here. All right. So step 1 DFP, like where I first have to give a diagram or picture of the situation, right? So first I'm just trying. I mean, it's a complicated situation. There's 3 objects in this situation that are being discussed. There's a river, there's a boat, and there's a river bank. And so they're gonna have to label these things with letters, and I don't want the letters to be confused right from the start. So I've got this river, right? I mean, so I've got 3 objects, and they each have a velocity that's distinct. So I've got like a river that's flowing to the northwest compared to the shore. I've got a boat that's going at some other direction, northwest compared to the river. And then I've got this shore, and the shore is not objectively still. I mean, the shore is like attached to planet Earth, and planet Earth is moving past the sun. And not that I care about the sun in this problem, but everything is in motion, right? Nothing is objectively or actually sitting still. Nothing is in physics in the world. Nothing is objectively or actually moving at any certain number. What anything is ever doing is compared to something else. Like that's the whole issue of velocity. That's what we're trying to see in all of our various forms of Galileo's principle of relativity. So here's my just general setup that I've got a river going like this compared to a shore. I've got a boat going like that compared to the river. And that's just a picture. Now, before I go any further, I'm gonna make letters stand for these objects because I'm going to start labeling velocities with subscripts. So I'm going to let W stand for water from now on. And then this is a little confusing. I apologize. But if I use R, then river and riverbank, it's easy to confuse them. And if I use B, then bank and boat get confusing. So I'm going to say from now on, S is for shore. The shore means the same thing as the riverbank. Riverbank shore. I probably shouldn't have used the word shore in the original problem, but I didn't. So whenever I say shore, I mean the same thing as the riverbank. I mean the land, planet Earth. And B, I mean boat from now on. Okay. So that's about like a picture of the setup. And now I'm going to do better than that. Like it was giving me all of these numbers and all these directions in the original problem. So let me sketch those out as velocity vectors now. So here they are. It told me in the problem that relative to the water, I'm just looking, it says relative to the water, the shore, the riverbank, is moving at 3 meters per second at a direction of 45 degrees southeast. So that white arrow up there, let me just make this clear. I'm not changing it, I'm just trying to make it a little bit clearer. Right? So the relative to the water, the shore is moving at 3 meters per second. So it gets a little arrow that maybe is 3 inches long, like as opposed to the other arrow that's representing 8 meters per second. So the other arrow should be like 8 inches long or whatever. I mean, these are obviously not perfectly drawn to scale, but so we've got a velocity vector that's like 3 inches long, and it's going down. It's going off to the southeast, 45 degrees south of east. So that is one velocity vector right there. Right? And what does that velocity vector represent? It represents what the shore is doing from the perspective of the water. It's not what the shore is objectively doing. There's no such thing as that. Right? Everything is a relationship. And it's not what the water is doing relative to the shore. It's what the shore is doing relative to the water. Because that's what the problem told me. In other words, if I were a little water molecule, if I was in the water watching, I would see myself as sitting still, and every other water molecule is like staying with me, sitting still. But I would see the shore going by me to the south east. Right? That's what that means. And it can I say more? So VSW means shore relative to water. And then I've got this other vector, VBS. This is boat relative to shore. According to the problem, now this is an easier one to visualize. This is if you just stood on the shore and watched the boat going by, right? So you stand on the shore and you think you're still, you think the land is still, but you watch the boat go by. The boat would go by 8 meters per second, like so a longer arrow, at 30 degrees northwest, right? Now, one thing I'm trying to emphasize here is it might be easier for you to picture yourself standing at the shore watching the boat, and that might be easier to picture than sitting in the water watching the land go by. But both are equally correct. There's nothing more true about one of those perspectives than the other. There might be something more convenient sometimes than for one, or there might be something more common about one, but they're both correct. All right, so we have these two different vectors representing these two different velocities. Let me also, I want to skip the page. I want to make something clear. Hold on. Note Okay, just note this. I mean, I'll just note this. All of the following, so there's like an instructor sidebar here. All the following phrases all mean the same thing. If I say relative to, or compared to, or in the frame of reference of, or in the reference frame of, or according to, or as measured by, they all are synonymous. They all mean the same thing. And they're all what we're trying to say when we write subscripts. If I say VA, if I write V, velocity, AB, I mean the velocity of A relative to B. Like, as opposed to, I don't mean the velocity of B relative to A, and I certainly don't mean the velocity of C relative to C. Or I mean, if I say VAB, I mean the velocity that B measures for A. I mean the velocity that B would observe if B regarded itself as stationary and watched A or measured A going by. That number that B would get is what I mean by VAB. In other words, whenever I write A and B could be anything. But if I write, like, in other words, I'm saying the order does matter. If I say VAB, I mean B is picturing itself as stationary and A is moving by it. And VAB is the number that B would get measuring the velocity of A, always. And okay, and again, remember, I mean, in a way, this is all so obvious to many of you in a way, but in a way, it's much more serious and universal than you might realize. Like, every time I say, if I say VAB, I mean the velocity that B would measure if B considered itself as stationary and measured A as A went by. So it's like from the perspective of B, right? And from the perspective of B, whatever B is, from my perspective, I'm never moving. Put it that way. It's like first person shooter game, first person perspective in video games, right? If you're in first person perspective, you're always you, and the world goes by you, right? And that is the way, the reason that works, and people like that in video games is because that is actually how we experience reality. Like a lot of that, like my nose is always in front of my eyes. Like my nose doesn't move away from me. I'm always with myself. The world is moving by me. So I always regard myself as zero and everything else is moving past me. Now you might say, okay, yeah, but what are you really doing? And my point is there is no really about it. Like, I might really be going 3 meters per second compared to planet Earth, but planet Earth is going 65,000 miles an hour compared to the sun, and the sun is going 650,000 miles per hour compared to the center of the galaxy, et cetera, et cetera. And that's not like a technical point. I'm saying I'm not objectively doing anything. What I'm doing is always a comparison to something else. That's the nature of velocity. So anyway, so VAB means the velocity of A as compared to B. Sorry. Okay. So that's just a language thing. So back to the problem. So here are my two velocity vectors that are given in the problem. Now, so that's step one, DFP. So step two, what is the question? The question that is asked in part A is it's asking, okay, what is the velocity of the water relative to the shore? But it only wants to know the direction. Remember, I mean, it's like a warm-up exercise. Like, remember, velocity is a vector. It has magnitude and direction. In this case, they're just asking what's the direction of the velocity vector, water relative to shore. That's what they're asking. What does the shore measure if it's watching the water go by? Now, no one ever told me that in the problem. What they told me is what the water measures as it watches the shore go by. But my step three, my GDP, my general definition principle is this is Galileo's principle for number 4. This is the two object case. Like, what is Galileo's principle number 4? It's what you watched the whole video about that many people said, I get it, but I don't see how to apply it to a concrete problem. Here we go. Here we're applying it to a concrete problem right here. Like, Galileo's principle of relativity is the mathematical way of getting across all of these velocities are relations. The one object case, the AA, if you only have one object, it's the first person video game thing. The velocity of a object relative to itself is always 0. Always. If you get that, you're getting part of what I'm saying about the relativity velocity. That's the one object case. I'm never moving relative to myself. But then the two object case, velocity of A relative to B, whatever A and B are, the velocity of A relative to B necessarily is equal to the opposite, the negative of the velocity of B relative to A. In other words, the velocity of me relative to you it's always the same number as the velocity of you relative to me. It's always the same speed, but it's in opposite directions. What the heck am I saying? I'm saying if you're standing on a platform and you watch the subway go by, if you're standing on a platform and you watch the subway go by at 50 miles an hour uptown, you're on the platform and you see the subway go 50 miles per hour uptown, then doesn't that mean that if you were in the subway watching the platform, you'd see the platform going at 50 miles an hour downtown, right? Like that's what you would see. That's what you would measure. Now you may say, well, that's an illusion. I say, no, it's not an illusion. It's just as legitimate as the other thing. The people on the platform see the people on the platform observe the subway going 50 miles an hour downtown. They might think that's like reality, but what is reality about it? The subway is on a planet Earth, and the planet Earth is going 60. Like it's not, the subway is not literally actually going 50 compared to the universe. It's going 50 compared to the platform uptown. But therefore, the platform is going downtown compared to the subway. That's as much reality as. Anyway, you want to let that sink in. But what I'm saying mathematically is the velocity of one thing relative to another is always the opposite of the other relative to the one. Again, you know this from video games, and you totally believe it if you play video games, which you should. No. But if you do play video games, you know, when you see the world coming at you this way and like you're running around or you're doing something peaceful like in Minecraft, like you're just walking forward and because you're in that, like obviously you choose that perspective, the first person perspective, and you're going forward and like like you just see yourself sit still and the world comes at you like this, right? But you know that is trying to represent the fact that from the world's perspective, it's sitting like that and you're going like that. I can't say it any better than that. But I'm saying that's not just an illusion and that's not just a video game thing or a movie theater thing. That's how the motion works in reality. So, all right, I'm taking way too long. So VAB equals negative of VBA always. So that's the two object case. Then the three object case gets more complicated. That's what we're going to do next. But that's the two object case. So in this problem, if they're asking what's the velocity, what's the direction of the water relative to the shore, I don't know offhand, but I know I was told that the shore relative to the water is going 45 degrees southeast. Therefore, the water relative to the shore must be going at 45 degrees northwest. That's what I'm saying. And if you get that, please know, when you don't get it, you don't get it. But once you get it, you might think to yourself, oh, that's all he's saying? That is so stupid. That always happens in physics. The minute anybody ever gets first you don't get something in physics. First it all seems stupid because it's so complicated. Then it finally sinks in and it gels together. And then people go, oh, that's so stupid. Like, oh, that's all that was? So people never give themselves the satisfaction of realizing that they just figured something out. In other words, what I'm saying, if you think it's stupid because it's so obvious, good, you get it. Don't criticize yourself or it. The answer to this, VWS must be going at 45 degrees northwest since VSW was going 45 degrees southeast. I mean, north is the opposite of south and west is the opposite of east. So that's the answer to that one. That's it. In English, from the perspective of the shore, the water is flowing northwest. By the way, that's why I drew my original picture like that. Because I saw that the shore was going past the river to the southeast. So I made the river go past the shore at northwest, just whatever that's worth. So that's the answer to A. It's just like a warm-up to see that you get the concept. It's technically GPR form number 4, case 2. That's A. Now B, so that's the answer. Now B, another sort of warm-up or piece to get you. B says, it's almost the same thing, but this time it's just asking about the number, not the direction. So it's asking, what's the shore doing relative to the boat? Well, I don't know offhand, but I was told what the boat was doing relative to the shore. the boat is going 8 meters per second relative to the shore. So if the boat is going 8 meters per second relative to the shore in one direction, the shore must be going 8 meters per second relative to the boat in the opposite direction. But so it's the same principle again, same GDP, same step three. Notice I'm not writing the steps anymore. Like I'm just going now. You have to write the steps in your exam, but I mean, I'm doing the steps. I'm just not labeling them. So this time it's not even asking direction. It's just asking magnitude. So if the boat relative to the shore was going 8, then the shore relative to the boat is going 8. So the answer is 8. Oh, sorry. So that's the answer, 8. Here. Oh, yeah, up here. Yeah. So the answer is right here. So it says so. VSB. That's what they're asking. Velocity of shore relative to boat is 8 meters per second. That's the answer to that one. Then this is where I did the instructor sidebar thing. So this is just a reminder, like, if you look, a lot of people, this is like everything in physics. For some of you, I'm sure you're thinking like, oh, that's all this is. Like, I've always known this my whole life. Like that may be for some of you. Now I'm just saying it's real science. But some of you, your heads might be swimming like, oh my God, S, B, B, S, A, B, B, A. Like, what the heck is what? I understand that. It takes some getting used to, and you do have to practice to get used to it. Again, if this is too much for you right now, when you practice or when you study, go back to homework 7 because it breaks it down more. But I am just trying to say A to B or S to B or B to S means B relative to S. The velocity of one thing compared to another is what we're talking about here. Okay, but I said that before, so that's that. Okay, now part D. Or is this now part? Oh, this is part C now. Part C asks something else that once you get it, it's very straightforward. It doesn't take a lot of work to once you get it. Part C asks from the water's frame of reference, at what velocity is the water moving? So the answer to that is 0. It doesn't matter whether we use the word water or we use the word shore or boat or whatever. If you understand case 1 of form 4 of Galileo's principle of relativity, anything relative to itself is always stationary. It's not moving. Nothing moves relative to itself. So that's why we say VAA equals 0. It doesn't matter what A stands for. In this case, A stands for water. The water is not moving past itself. You might say, wait, but I thought there's a current. I thought the water is moving. Well, the water is moving relative to the shore, but it's not moving relative to itself. Just like the earth is moving relative to the sun, but the earth isn't moving relative to itself. Otherwise, you'd be falling down all the time. I can't say it better than anyway. So that's C. The answer to C is 0. Now, then we get to D. D is where we have 25 minutes. D is where the real work and the real thought comes in. We got to do a lot of work to do. D asks, from the perspective of the boat, what is the water doing? In other words, it's asking, what is VWB? What is the velocity of the water relative to the boat? Now, that is not obvious. That's not given. We're asking for a velocity here, so we're asking for a magnitude and a direction. We have to get both, like i.e., we're going to have to get a number of meters per second, and we're going to have to get an angle. Okay, and what's going to happen here to get this is we're going to have to add together the two velocities that we do know to create the third velocity vector that we're trying to find out. So in principle, what's going to happen here is we're going to do all the same kind of work, the same method that we did last class on Wednesday. There, we did it with displacement vectors. Here, we're doing it with velocity vectors. Same math, but it's harder to picture in your mind what it means, what we're doing. It's hard, it's easier to lose sight of the big picture now that it's velocity vectors, which is sort of why we just did those warm-ups. So it first asks you the question to like find the answer graphically, to like make a picture showing what's going on here. So here is my picture. Let's go back to is there anything in the chat? Okay. Wait. Okay. Okay. So we have to get VWB. We're going to add two vectors together to get to VWB. How do we know what vectors to add together? Well, this is specifically where GPR form number 4, case number 3 comes in. This whole VABBC, VAC thing that is confusing to a lot of people at first. Like, first I'm just going to say, problem solving wise, the VABBC, VAC, it doesn't matter what A, B, and C stand for. They could be any 3 distinct objects. What you're trying to see is the pattern of how the A, B, C are lined up. Like the rule is, if you want to get A relative to C, you have to add AB. You have to add A relative to B relative to C. You have to go in that order to get that kind of answer. What I'm saying problem solving wise is if I want to get WB, the way to get it would be, for example, there's many ways that are correct, but there's a lot even more ways that are incorrect. One correct way to do it would be VWS plus VSB equals VWB. Like, where did I get that from? Like that, I'm just following the pattern. That pretend that the letters were A, B, and C. I'm just using W, S, and B instead of A, B, and C. I'm saying like VAC equals VAB. Like, look at the pattern of the letters, or look at the order in which they're written. If you want to get A to C, you got to add together AB to BC. What does this mean physically, conceptually? Again, it's like saying, if I want to know the velocity of me relative to Manhattan, one way to get it is the velocity of me relative to Subway plus the velocity of Subway relative to Manhattan. That's why I ride subways, right? That's what we're saying here, except now it's in 2 dimensions, so it's a lot harder to picture. That's like why we have to do the work. But so the first thing I'm saying is to know which vectors even to add together at all. I'm using GPR form number 4. VWS plus VSB equals VWB. And those are 2 known quantities. I just figured them out in the warm-up earlier questions. I got the velocity of WS and I got the velocity of SB, so I can do this work now. So I put them together in a picture. I say, okay, I'm going to draw them tip to tail just to see what's going on. VWS is going northeast at like this 45-degree angle, and it's short. It's like 3 meters, right? Then VSB is this long 8 meter per second thing going southeast at a 30-degree angle. I think it was 30. Yeah. So I draw them tip to tail. I put the tail of the second vector at the tip of the first vector. And the answer that I'm looking for would be the vector that completes the triangle. Like, this is the answer that I'm looking for. Is VWB. Notice if now this is just a sketch. If I drew this somewhat to scale, somewhat accurate, if I actually had used a ruler and a protractor, then the length of that red arrow will be the answer. Like, I literally measure all these things, and the length of the red arrow, the missing red arrow, would be the answer, the speed that I'm looking for. And the angle of the red arrow would be the direction that I'm looking for. Like, if I literally drew this perfectly, then I could just measure the red and that would be my answer. But I didn't draw it perfectly. I want to be able to do this analytically. So what we're going to do for the next 20 minutes is actually do the numbers, compute them. But stop me if it's not clear. What we're looking for is the speed and the direction of what the water is doing relative to the boat. It's if you stood in the boat and watched the water go by, what would you see? That's what we're getting. Like, if you stood in the boat or sat in the boat, you don't see the boat moving relative to yourself, right? Like, you might believe that the boat is moving, but that's not what you would observe or measure. The boat's always with you. You see water moving past you in a certain direction at a certain speed. That's what we're trying to figure out here. What speed and what direction do we see the water moving if we are the boat? By the way, if we stood on the shore and watched the water, we get a totally different number, right? In fact, we get the yellow vector. We get 3. at 45 degrees northwest. We already know that. We're trying to get what the boat would see the water doing. So how do we do it? So just like Wednesday, first we draw tip to tail to get a sense of what's going on. Now we're going to use the component method. We're going to zoom individually into each vector by itself. We're going to take each individual vector and break it up into its individual X and Y one-dimensional components. What we're doing now, when we do the component method, so it's exactly like we did on Wednesday, it just may seem more abstract now. What we're doing when we break things up into components, we're really using GPR form number 5. We're saying that each two-dimensional problem is really two one-dimensional problems occurring at the same time, but independently of each other. So we're going to take each two-dimensional motion and say, but that's really two separate one-dimensional motions that are not messing each other up. Like, for example, the first vector, the water is going 3 meters per second relative to the shore. It's going off in a northwesterly way, like 45 degrees northwest. So what we say is, oh, well, when you're going 3 at 45 degrees northwest, what you're really doing is going some amount west while you're going some amount north. So let's break it up. Notice I break it up not just into a random geometry triangle, but into a physics vector triangle. Like I'm going to look at I'm intentionally taking each vector and breaking it up, making it into its own right triangle. It's always the original triangle that this situation gave me is not a right triangle. It's going to be hard to analyze that, especially if there were more than 3 vectors. It'd be really hard to analyze. But I take each vector and I turn it into its own right triangle. I can always do that because I'm saying each two-dimensional motion is really the sum of two perpendicular one-dimensional motions. And so I literally do tip to tail. I'm always going to break everything up into first a horizontal. I always draw the horizontal first. Pro tip, if you're still paying attention to me, if you're still listening, especially if you sort of know what's going on. But you do want to practice this. Breaking up vectors into their components, there's lots of choices. I'm making it look like there's only one choice. There's only one choice that works really well, but there's other choices you might make on your own if you practice this on your own. And my advice, the pro tip is, whenever you break a vector, whenever you turn a vector into the hypotenuse of its own right triangle, always start by drawing your horizontal leg. Always draw the horizontal. Again, this is not a physics law. This is a problem-solving strategy. Always start with your horizontal leg first. And definitely make arrows. I will take points off if these are just raw geometric triangles with no arrows. The whole point of all of this is vectors and directions. So you're always drawing arrows. Always draw your horizontal arrow first, and from the tip of your horizontal arrow, start the tail of your vertical arrow. That is a strategy that will never let you down once you get used to it. So this is why I always say to go northwest is really to go some amount west while also going some amount north. I say it like that on purpose because I draw the horizontal first, then I draw the vertical. Why do I do that? Because that will ensure, if I do it like that, it'll ensure that every angle that I end up measuring is always like a northwest, like it's always every angle between the two tails. Every angle that I look at will be between the two tails of the vectors, and it will be measuring how far north something is going compared to west, or how far south compared to east. In other words, it will always be end up measuring in the natural way, in the way that we talk. I'm not going to over-explain this, but my advice is, so I always draw the horizontal first, and then from the tip of the horizontal, I draw the tail of the vertical, and I say, okay, when you're going northwest, you're really going some amount west while you go some amount north. Well, how much of each one are you going? So when you go northwest at a certain rate of speed, you're really going a certain rate of speed to the west while you're going a certain rate of speed to the north. How much? We use SOHCAHTOA. The adjacent leg of this triangle comes from cosine, and the opposite leg comes from sine. The adjacent leg is hypotenuse times cosine of the angle. The opposite leg is hypotenuse times opposite times sine of the angle. So when you go 3 meters per second, when you go 3 meters per second to the northwest at 45 degrees, what you're really doing at that moment is you're going instantaneously 2.12 meters per second to the east, to the west, while you go at that moment 2.12 meters per second to the north. That's what I'm saying. I can't say, I mean, I can't say it any more clear than that. So those are the two components. The x component of your velocity is 2.12, and the y component is also 2.12 because it's a 45-degree angle, so the sine and cosine are the same. So I leave that. Now I go to the other vector. I now zoom in on the other vector. The other vector was 8 meters per second to the southeast. So I do the same thing. I break it up into two sides. It's a little sloppier here. I apologize. But it's the same concept. I'm saying you get the x and y sides of the triangle, that to go north, south, east is really to go some amount east while going some amount south. How much east? Well, hypotenuse times cosine. How much south? Well, hypotenuse times sine. And those are numbers. The number 8 times cosine of 30 is about 6.93, and the number 8 times sine of 30 is about 4. Those numbers represent velocity components in various directions. Now, there's 12 minutes left. What do I do? Why did I do all this? I just took two individual velocity vectors. I have not added them together at all yet. What I did was I took each velocity vector and broke it up into its individual perpendicular components, just like I did last week on Wednesday. All I've done so far is recognized that some kind of two-dimensional motion is really two one-dimensional motions happening at the same time, but independently of each other. Why am I saying independently of each other? Because this is the whole key. And this is what you were really seeing in lab 3, whether you knew this is what you were seeing or not at the time. What we're saying is, oh, so the first velocity took me some amount, I was running at some rate to the west. The second velocity vector has me running some amount to the east. Now, those two numbers relate to each other. East and west can be added together, or east and east, or west and west. You can't add east to north. It has not, they're independent. But you can add, in other words, in this case, the shore sees the water going some amount to the west, at some rate to the west. But the water, sorry. Sorry, let me say that differently. I'll say it like this. According to the boat, the shore is going some amount to the east. According to the boat, the shore is going some amount to the east. But according to the shore, the water is going some amount to the west. So whichever number is bigger is going to win, so to speak. Like at the end of the day, if what we want to know is what does the boat see the water doing, we've got to add those two things together. What we can add is, so we make a chart. We can add all the X numbers together independently. We can add all the Y numbers together independently, just like we did yesterday with displacements. It's just harder to picture with velocities. So I make a chart. I always make an XY chart. So I say, okay, water to the shore, it took me to the west 2.12 meters per second. West, on that axis, west is labeled negative, east is labeled positive. So I put a negative sign there. The water is the shore observes the water to be traveling at 2.12 meters per second to the west, so it gets a negative sign. The shore also sees the water traveling to the north, 2.12 meters per second. So that got a positive sign. So I'm just putting the numbers in the chart. And now what do I do with those numbers in the chart? I literally go down the columns. I'm adding up the numbers, but one column at a time. So negative 2.12 plus 6.93 gets 4.91. What is 4.91? It's the number of meters per second that the water is traveling relative to the boat in the x direction, i.e. positive 4.81 meters per second means to the east. At the same time, the water is moving at 1.88 meters per second to the south, hence the negative sign, right? That like, oh, okay. So what do these numbers mean? Like, how is this an answer? Is this an answer yet? It's almost an answer. It's not a final answer yet. What it means is at the end of the day, after I've done, so now I've done the addition. First, I took the vectors and I broke them up into individual components. Then I put down the components like into my chart and I added up the components one dimension at a time. Again, this whole concept is you can only do physics one dimension at a time. So I did the addition in one axis at a time. Now I've gotten to almost final answers. I'm saying in the x-axis, the water is going at 4.81 meters per second to the east. In the y-axis, it's going 1.88 meters per second to the south. So I put those two things together into one big triangle, right? Like that one big final right triangle. So everything is right triangles because everything is two perpendicular axes of space. So at the end of the day, the water relative to the boat is going 4.81 meters per second to the east. And while it's going 1.88 meters per second to the south. So I drew the horizontal first. I went over to the right because it's positive. Then from the tip of that horizontal vector, I started a vertical vector. I put the tail and the vertical goes south, right? Notice all of this has arrowheads. It's all tip to tail addition. You've got to have tips and tails on every side of every triangle. Otherwise, it's not physics. So at the end of the day, I have a final right triangle. I can apply Pythagorean theorem and SOHCAHTOA to this final right triangle. I could say at the end of the day, the speed, the magnitude of the velocity vector, VWB, is the Pythagorean sum, the square root of the squares of this side and that side of the two legs. So at the end of the day, the water is flowing past the boat at 5.16 meters per second. That's a rate of speed. If the boat looked at the water, the boat is observing the water going 5.16 meters per second. Like not 3, not 8, not 11, not 5. Like it's a complicated number. You can't just do it in your head. Like we're adding 8 plus 3 and getting 5.16, which just goes to show you we're adding vectors. We're not just adding raw numbers. We're taking into account direction. So at the end of the day, the boat would look at the water and see the water going 5.16 meters per second. And in what direction would it see the water flowing? It would see the water flowing at 21.3 degrees southeast. Where did I get that? I did the arctan, like TOA, tangent of angle equals opposite over adjacent. I most certainly have a right triangle here. So the angle I'm looking for is that theta labeled between the tails. So the tangent of that angle, I guess if you want me to add a step, like the tangent of that angle would equal the opposite over the adjacent. Therefore, the angle itself would equal the arctangent of the opposite over adjacent, right? I don't want the tangent, I want the angle. So the angle is the arctangent or the inverse tangent or tangent to the -1 of the opposite side, which is 1.88, over the adjacent side, which is 4.81. So on my calculator in degree mode, I get 21.3 degrees. And I know it's southeast because I've taken all the pictures and the arrowheads seriously. The yellow line is going south of east. Yeah, I mean, it's going south and east. It's going south of east. So this yellow line in this triangle and this angle is my final answer. The question was, what is the velocity of the water relative to the boat? Velocity has two pieces to it: magnitude, i.e. speed, and direction, i.e. angle. There's my two answers. And notice one last thing. Obviously, class is about to end. But notice one thing. This final answer that I got, this yellow line, this is that red line in this picture. Like this red picture or this picture predicted that I would get some kind of arrow going to the southeast, some kind of arrow that's bigger than 3, but smaller than 8, right? Like somewhere in between, like bigger than 3, but smaller than 8. Well, sure enough, that's what I got. Like my final answer is that red arrow in the original picture. Precisely speaking, it's 5.16 meters per second at 21.3 degrees southeast. So that's how you do that problem. That's a lot, I think. It didn't make any sense to me when I first did that. I mean, obviously that was years ago, but if you practice and if you want more practice, if you want to try something that's like this, but you want to save this one, again, go to the second to last page of homework 7 and see if that page now with the Toyota and the Pontiac or whatever, see if that page makes more sense to you now that we've just done this. And or go to the practice exam, see if you can do this problem without looking, see if you get the same answers that I just did, et cetera, et cetera. And there will be a problem like this on your actual exam. Now, there's also more to this problem. I know there's more questions, but I'll answer those quickly, probably on Wednesday, and or you can check past videos to see those. But I think the meat and the heart and the hardest part, the part worth knowing, I mean, the part really worth practicing and wrapping your brain around is the part we just did. And last thing too, you got to practice. I'm telling you that I don't think this is easy. I mean, if you do think it's, well, I don't think it's easy, but also I'm trying to walk you through and do it sort of like I'm trying to do all the triangles in the best possible way. But until you practice on your own, you don't realize that, like, for every triangle you draw, there's a lot of choices and a lot of different ways that you could do it. You want to practice on your own to see what choices I've tacitly rejected and what choices I've made to make these triangles. Again, in other words, every time I draw a vector, then I break it up into 2 parts, a horizontal part and a vertical part. And I always draw the horizontal first, and then I draw the vertical, and I always then make them put together tip to tail. You gotta practice, is all I'm saying. Okay. But that's it. I mean, actually, you're ending 2 minutes early, so I'm gonna stop. I'm gonna hang out here for any questions or concerns or anything, but I'm gonna turn off but if there aren't, or have a great lunch or a great day, and I'll see you Wednesday. But I'm stopping the recording and I'm hanging out. And obviously I'll upload all